Sophia, Corina, and Eric joined since the last community meeting. Please welcome them. One big issue I think many people are asking about is the standard library refactoring, right? We move its results about basic types that are defined in core from STG to the core library, right? Basic statics and supports for code actions and so on, all to the main repository, right? The main motivation is you want the basic types defined in a single place. It was very confusing for some users because some of the results were in core, some of them were in STG, and other results about this about natural numbers you have then spread over 3 different repos, right? And was not easy to have a consistent simple normal form, right? The repos were having different views of what the normal form should be. Sometimes standard was overriding the behavior of the core. It was really confusing, and the user experience was not great. So we decided to centralize everything in core about basic types. Also, some features some users did not know they existed, right? We met users that were completely unaware that Lean has support for code actions, right? They were only enabled after you import STG, something called actions, or some key tactics were not available in core. For example, Omega, we want to have it available for termination checking, but it was only defined as in STG, right? Same thing for simp question mark, exact question mark. Some users were not using STG. They were puzzled why I don't have simp question mark, right? And also accelerated developments, right? So with these things spread over multiple repositories, a lot of time was spent moving, checking, propagating changes. Well, we noticed a big increase in the speed of developments after we centralized the basic types and tactics in the core repo. But then the question is, what about standards? What's going to happen with these standards, right? First thing, a lot of work still needs to be done. We're still cleaning up standards, right? We still have to upstream some lemmas about the primitive data types. We're trying to ensure we have consistent simple normal forms in the core Lean and Mathlib, right? Joe Hendricks is working on tools to ensure the simple normal forms are not modified by Mathlib. All users have a consistent simple normal form for the basic types. In the STG, we expect it to have in the future additional types like the red-black map, red-black trees, hash maps, and so on, a regular expression library, support for async I/O, networking library, internet protocols, and domain-specific annotation extensions, right? This is going to be the scope of the standard library in the future, after all this refactoring has been done. The many improvements on the language server, right? Mark improved many things, but one thing that I think most users would appreciate is the auto-completion performance, right? Before, if you imported Mathlib, in some machines would take a long time to get auto-completion. We now observe like 10x improvements in many auto-completion operations, right? Almost everything is instantaneous. It's great improvements overall. Another feature that many people wanted, right, was to stale dependency notifications, right? It's very common you go to a file, it has a stale dependency, and you're completely unaware. Now you're going to be notified if this happens, right? This is a great improvement. There are many other improvements, like better auto-completion, consistent auto-completion overall, right? Especially for the imports, auto-completion improved a lot recently. Little things also, I mean, sometimes when you see the call hierarchy, you would see the internal private name of a declaration. Now they are properly displayed, right? Overall, There are a bunch of improvements like that, but overall the experience is much better, right? Especially for someone that's using VS Code. Another feature that some of you may appreciate, is that you can control the display of big terms in the info view. We had users complaining that if the term is huge, right, they apply a tactic that produces a huge goal. It would take a long time just waiting for this gigantic term to be rendered in the info view, right? You can control now with deep terms, right? This new option, deep terms, and after a specific depth, you can set with the deep terms.threshold. You can will suppress the big terms. You put the 3 dots, but if you hover over the 3 dots, you'll be able to see the term, right? And of course, if it's another deep term, you're going to see 3 dots there, and you can keep hovering over the 3 dots and keep going deeper and deeper if you want. Omega now is in core. This is great, right? It's used by the termination checker. It's also used by default for array indexing proofs, right? There is a preprocessing tactic called BV Omega that will reduce. If you have bit vector problems, some of them can be translated into integer arithmetic, and BV Omega will do that. BV Omega also now supports the fin type, shift operators. There are many improvements, right? Also in performance, right? Omega was using definitional equality to check terms that were definitionally equal, and this was causing problems in some big goals. This has been fixed. Another feature is termination by, right, question mark. If you use termination by question mark, now you get a code action, right, that suggests you to a concrete termination by. The point here is that instead of trying to guess every time why a function terminates, it allows you to put in your file the reason why it terminates. For this particular example, it's not a big deal. Link can quickly guess the right reason why this function terminates. But if you have a really big example, right, it may help, right? It may speed up when you compile your file again, right? Lean will know exactly why the function terminates. It doesn't have to keep guessing over and over again. And can also give you insights why the function terminates, right? It can also clarify to you why the function is terminating. Another cool feature is functional induction principles, right? If you have, especially for mutual recursion, but this it can be for anything. It can be for if you have a complicated, well-founded, a complicated function defined by a well-founded recursion, Lean can now generate an induction principle for reasoning about this function. But let's focus on this example here. We have these 2 mutual recursions, right? And we can now ask Lean to generate, for example, induction principle for replace const, right? And Lean will generate this new induction principle, right? That has 2 motives, because it's a mutual recursion between these 2 functions, and so you have a motive for each one of them, right? The first motive is for replace const. The second motive is for replace const list, right? You'll notice that in the first one, the recursion is on term. The second one is a recursion on a list of terms. And you have 5 cases, right? And notice that you have only 4 alternatives, but in the first alternative, you have an if then else, right? And here, you have 1 case for the then branch and 1 case for the false branch. Roughly, you can view each case in your induction principle as a control path in your function, right? And basically, that captures all the cases that you need to consider when proving things about replace const. And it's exactly the case. Suppose that you want to prove that if you count the number of constants after replacing a constant, the number of constants do not change, right? you can prove now, well, it's a very compact proof. Before would be a mutual theorem, right? It would be a theorem with a lot of boilerplate codes. Now, just applying induction principle, you can prove it with SIMP, right? This is great. And that, for users that are using mutual recursion, this is a time saver. We added, in the last community meeting, we mentioned that we had SIMPROX. Now we have also GSIMPROX. GSIMPROX are SIMPROX that's produce terms that are definitionally equal. They are great for using with SIMP and GSIMP. And for SIMP, they are useful because, for example, suppose in this example here, we have this write function, where the first argument that has a false dependency, right? You have this natural number n, but there is another argument that the type is bit vector of type of size n times 8, right? If you replace, suppose that you have 0 plus x. If you simplify 0 plus x with x, you cannot, simply will not do it there, the replacement, because each would have to add a typecast, right, for this argument that depends on the first argument. But if you're replacing by something that's definitionally equal, you don't need a proof, you don't need a typecast, and we have users that needed this feature, right? For example, if you apply now a simp or GSIMP over this goal, it's going to simplify the first argument, right? You have this first argument where you have 2 times 8 times 8 divided by 8, it will become 16, right? So this is great. I mean, we have now, when you just find your simplification procedure, you can control whether it's producing a proof or what's there. It guarantees to produce only definitionally equal terms. And of course, it works for SIMP and GSIMP, this feature, right? Another feature we added is the macro letExpr and matchExpr. It's just simply for people that are writing meta programs, right? matchExpr is a very simple macro. It's useful only, the name is matchExpr, but right now it's basically matching expressions, right? Sorry, matching applications. And there's no support for nested applications. It's very light. You have here is matching if E is an application of EQ. These are pattern variables. That's why they are in blue, alpha, A, and B. matchExpr will consume metadata, annotations like optparam, and will instantiate meta variables if you're in a monadic codes, right? If you're in pure code, it will take care of the metadata and annotations like optparam, but it will not instantiate meta variables because it doesn't. In pure code, you do not have access to the state where the meta variables are. We have the assignments for the meta variables, but it allows us. This structure allows us to write more compact codes. A lot of sharing happens here. For example, one pattern we used to have in the past was to use get function and arguments that would return a pair of a constant and an array containing the arguments. This was bad because first, you're locating an array. Second, you would be incrementing the reference counter of all arguments. Here, for example, if you have arguments that nobody cares, like you putting underscore, these arguments will not even be touched, right? You will not increment the reference counter and have to decrement it later. There's no extra memory being allocated. And letExpr is just syntax sugar for matchExpr, right? With one case. Basically, for example, here, letExpr nats alpha, arrow alpha here is just equivalent to matchExpr alpha with one case nats where you have the continuation and the else case is a failure, right? One motivation for having this let expert and match expert is to make it easier to define simprocs, right? For example, we can write a simproc now in a much more concise way. And issues like, oh, I forgot to instantiate the meta variable, or oh, there's metadata there, that's noise. Now you can write in a much more compact way your pattern matching. Another thing we have fixed recently was when we were pattern matching built-in literals, like for example, bit vector literals, the equation lemmas that were being generated were exposing the internal representation for bit vector literals, right? You would see in the equation lemma something like bitvec of net of thing make of would have the full expansion of how these bit vector literals are represented using constructors, right? And what would happen in practice that you would not, the lemma would not even fire when using simp, right? And now you get what you wrote, right? You have the bit vector literal there. In your equation, you get exactly the bit vector literal you wrote there. Simple had many new features and bug fixes. I mean, I try to put some of the fixes that have been added, pushed in the last month. But I will highlight only a few of them. One of them is the zeta delta option that the community asked. The idea is to distinguish, before we had only zeta, right, that you do these two transformations here that's in the bullet points, right? If you had a let inside of your goal, it should reduce the let, right? You have let x equals val, e that depends on x, it should reduce to e now with x replaced with val, right? You unfold the let. And we also had the case where you have in your local context x that is a let variable that's abstracting val, and you want to replace equivalences of x in your goal with val. Before zeta would do both, but the community wanted zeta true to be true by default. That's all, the lets would be in your goal would be expanded, but the x's that have been abstracted, the community didn't want them to be unfolded by default. Sometimes you are carefully written, right? These abstractions, and you don't want to expand them eagerly, right? So in the new default now is zeta delta is false by default, and zeta is true by default, right? Simple, right? And you can control, right? If you don't like the defaults, you can write your own macro that sets both to true like it was in the past, the behavior you would observe in the past. But let's see in action how the new behavior, what new behavior is. Suppose that we have this example where we do an intro x, right? After doing intro x, we would see at the simp, before executing simp, this would be the states, right? You have x is 5, and you have our goal is let y equals 4, x plus y equals z, right? With this change, if you perform simp there, it will simplify the lets, but the x will not be unfolded, right? If you want to unfold x, you can provide x as a parameter in square brackets to simp, or you can say simp zeta delta equals true, it will unfold the x. Another issue that was affecting the community was how we index local hypotheses, right? We use indexing now in Lean 4, right? We have discussed that before. But what happened is that in many cases, you would have a hypothesis that's not has not been simplified, right? For example, and if you try to index the left-hand side of age, right, would have in our index saying, oh, it's the f, where the first argument is a prod make of two variables. The second one is a projection of a prod make. And that would what would be in our indexing data structure. If you try to look for instances of this left-hand side, you will not find any, right? The second argument here, B, is not a projection of a prod make, right? And we would not use age, right? And many people were sad about that, right? It should force the user to simplify the hypothesis before, sorry about that. Would force the user to simplify the hypothesis before applying it here. So now we change. I mean, the indexing was motivated not for, usually you have a handful of local hypotheses, right? The indexing is really useful for the global theorems, right? Where you have tens of thousands global theorems, right? Usually we don't do indexing for local hypotheses anymore. It's just very light indexing based on the root symbol, like we're doing in Linktree, and you get now exactly the behavior people were using in Linktree for local hypotheses. This example now works as people expected, like it did in Linktree. We also now have the LeanSat repo, right? Is getting better and better. But today, you can already use it to invoke a set solver and discharge goals having Boolean expressions, right? For example, you can prove the simple facts here using set decide. Basically, what happens here, there is a conversion to CNF that's verified, right? Then we call a set solver. The set solver produces something called LRATs certificates that will have a verified checker in. This verified checker is executed using native codes, right? And that's basically what happens behind the scenes when you're using set decide. These are for users that are trying to discharge big Boolean expressions using a set solver. We're going to use it for bit blasting, right? We're currently working on a verified bit blaster for bit vectors. And in the future, we're going to have something like BV decides that will allow us to discharge bit vector problems using a set solver. In Lake now, soon we're going to have a tone configuration file. Many different people in the community asked for this feature, and it will be available in the next community meeting, right? We are all excited about having support for TOML-based configuration files too in Lake. And we believe many people in the community will be happy with this new feature in Lake. About Verso, I will invite David to talk a little bit. I mean, there are many exciting news in Verso, but David, do you want to say to tell us about Verso? Yeah.
Sure thing. Yeah. So some progress that's been made so far since you last saw a demo. The first is that it now can render proof states similarly to how Electron does. So you get a little lozenge. And all of the scope-aware highlighting that the compiler produces also works inside of rendered proof states. So if you take a look at the screenshot here, unfortunately the mouse pointer wasn't included, but you can deduce from the fact that there's a little hover box saying NAT that the mouse is pointing at the 2 next to the hover box. And you can also see that other occurrences of this variable 2 are also lit up. So it's aware of which variables are identical and can guide you toward understanding things that way. That was fun to implement. So we're well on our way toward having interactive books. Not quite there yet, but progress is being made. Next slide, please. When you start writing a big interactive book, though, you run into an issue, which is that a new version of Verso comes out, and a new feature was added to Lean to support it doing something cool. But that means that in order to upgrade to the new version, I'll have to upgrade my Lean. But oh no, I have a lot of example code in this book. What am I going to do? Well, the answer is that now you can take that example code and put it in a program that's processed with the older version of Lean, and you can mix versions of Lean. And the way this works is that all of the code-aware things, like the highlighting generation library, was extracted into an independent library that CI verifies works with Lean 4.3 and up. I plan to have as wide compatibility as is practical given resources on that one. I think I'll get a more clear picture of that as time goes on, but so far it hasn't been a big challenge to make it work with lots of versions of Lean. Then there's a Lake facet, which generates JSON representation of the code examples that you've annotated in your original Lean files, and then a little library that automates the extraction of that into a big JSON file, which you can then load up into your book file. So you could be compatible with many versions of Lean all at once, and also be a little bit more flexible about how you develop your code and what order you put it in. The order it occurs in the book doesn't have to match the order that it's in the files, and so on and so forth. So this looks a lot like the back end of the functional programming Lean build process, except now it's all nice compiler internals rather than hacky Python regular expressions, which will be nice in the long run for maintenance purposes. And if you want, you can follow along. If you think you could use this for your library, you can follow along the new repository we made there, because I could see this being useful if you want to make slide generators or something like that as well. And then finally, one big downside to the way that the system was implemented before was that if you had a single parse error, it would give up and say, and that's no fun. So I added sort of very low-level parser error recovery to Lean's parser framework, which is a little bit too low level to be hugely useful for actual Lean code, but it's quite nice if you're doing some kind of embedded language. And in this particular case, it allowed me to add parser error recovery. So now you can get multiple parser errors out of one Verso document, which is nice. And even more so, the system continues to work after those parser errors in many cases. So, for example, the code action to transform that bulleted list into a numbered list is still functional in this screenshot, even though there's 3 parser errors. Thanks.
Awesome. Great. This is, now we have plenty of time for questions. Feel free to ask. Let me maybe stop the recording for the